Windows Kernel Graphics Driver Attack Surface by Ilya Van Sprudel.
Okay, looks like that works. Awesome. So yes, I will be talking about Windows Kernel Graphics Driver Attack Surface. As just mentioned, my name is Ilya Van Sprundel. I am the Director of Penetration Testing at IOActive. I do penetration testing, code reviews, lead teams, basically break stuff for fun and profit, and sometimes advise on how to fix things. Right, so let's dive in. What's my agenda basically? So I'll do a slide about what this thing is about, and then we sort of gives the 50,000 feet view of what these drivers are like. And then I sort of dive into the entry points where I say, well, there's entry points, and these are the conditions under which these entry points can be entered into. And then once that's covered, and so how do you get there how do you get to the kernel stuff from userland? And once I cover all that stuff, I'll do a demo of a tool that shows how this thing works. And then the last part, sort of putting it all together, is where the fun begins, where I'll talk about how to fuzz these things, how to reverse engineer them, and I'll do a small demo of how to fuzz a driver. So what does this talk about? Well, it's, as the topic said, about Windows graphics drivers, specifically WDDM graphics drivers. That's the Windows Display Driver model, which is a new driver model. And I'll talk about that in a few slides. As for the audience, or the target audience, I guess people that want to audit graphics drivers, the perfect target audience, but also developers. I mean, if you're a developer, it's nice to know what the attack surface is. There's a fair amount of developer documentation, and it tells you how to write a driver, but it's not written for hackers, so it doesn't tell you this is attack surface, this isn't. So I'd like to believe that my presentation gives you better coverage on that. So if you're writing graphics drivers, I'd like to believe that this is also useful to you. And the other target audience is just generally curious people, right? If you want to know about the Windows kernel or something like that, then there is hopefully some interesting stuff in this presentation. As for knowledge needed to follow this presentation, some basic knowledge of Windows kernel stuff is useful. Since it's not that much like other Windows drivers, it's not necessary, but it's useful to understand some concepts. Right, so Windows graphics drivers. There's two models. There's the old model before Windows Vista and the new model, WDDM, after, or Vista and onwards. The old model is called XPDDM or XDDM. It's Windows 2000, Windows XP. It's legacy. It is no longer supported as of Windows 8. And it's not stuff I'll cover in this presentation. It looks completely different, and so I'm not covering it. I will be covering the attack surface for WDDM drivers, or Windows Display Driver model. And so the first version of that came out with Vista, and then when 7, a more evolved version came out. In Windows 8, they added a bunch of new features, and 8.1, a number of other features got added, like Miracast and those kind of things. I won't obviously describe the entire model because we'll be here a week from now. But I will describe the parts that are interesting from a security perspective alone. If there's anything like driver-wise that you have questions about or not quite sure about, the documentation is actually pretty good. It just doesn't focus on the security part. So before we dive into specifics, who actually makes these things? Because it turns out there's a pretty large number of graphics drivers. Obviously, the individual hardware vendors, right? NVIDIA, AMD, Intel, Qualcomm, FIA, Matrox, and so forth. They make drivers, and those are the ones that usually expose a lot of attack surface because they're very rich, right? Because they expose all the magic of these cards, right? And as we know, graphics cards nowadays are very, very advanced pieces of hardware, and so the drivers for those are generally very rich. The images for these things will generally be several megabytes large, and while that might not mean much, for a graphics driver to be 10 megabytes, or for any Windows driver to be 10 megabytes is enormous. It means there's a lot in there. So that obviously those are the drivers that we know. There's others. Obviously there's the basic fallback. This is sort of the bare minimum display driver. This comes from Microsoft. This comes in box with Windows. If you have no graphics drivers, you fall back to this. There isn't much there. I've looked. I wouldn't worry too much about those. It does the bare minimum. And you see that because your graphics kind of suck when you end up with those drivers. And then there you have sort of the special purpose drivers, right? So, for example, virtualization, each virtualization software comes with its own Windows guest drivers. So VMware has them, VirtualBox has them, Parallels has them, and pretty much all of them have them. If you have a Windows guest, they'll have sort of the guest install additions, whatever. they'll come with a graphics driver. And they're usually a lot thinner than the individual hardware drivers because they have like one narrow purpose, right? And then there's a few others, right? There's stuff like virtual display. And these come from like smaller companies. Again, these are usually relatively small because they have like one narrow purpose. But they could still, they would still expose interesting attack surface, right? Okay, so let's talk about WDM. WDM is sort of, it's a split model where as much of the driver as possible runs in userland, and then the bits of the driver that can't run in userland end up in kernel. At least that's how WDM was designed. And so there's this model where userland talks to kernel, and I'll talk about that interface in a lot more depth later on. And so this move was done for stability and reliability. And I found this really, really awesome quote on MSDN about why it was done. It says, in Windows XP, display drivers, which are large and complex, can be a major source of system instability. These drivers execute entirely in kernel mode, deep in the system code, and hence a single problem driver will often force the entire system to reboot. Basically, you get a blue screen, right, if something goes really wrong. It says, according to crash analysis data collected during the Windows XP timeframe, display drivers are responsible for up to 20% of all blue screens. That is throughout the Windows ecosystem, right? 20%, and that's with the old model, XPDDM, right? Because everything ran in kernel, and so one single mistake anywhere, you get a crash. And so WDM set out to change that and said, well, what we're gonna do is we're gonna take as much as we can, move it into userland, and then if you get a crash there, then the process just crashes and you could restart and it starts over, but you don't take the system with you. And only the parts that have to run in kernel, the things you can't do from userland, the privileged stuff, only that will run in kernel. It's not to say that the userland drivers don't have interesting attack surfaces. I mean, they do, right? There's encoders and decoders in there. They can have like binary planting attacks. Some APIs may be indirectly exposed through the web, through stuff like WebGL. So the user mode stuff still has interesting attack surface, but it's not what I'll cover in this presentation. I'll only focus on the kernel mode stuff, where we know where the interfaces are relatively well defined, and we know we can pick and point and say that's attack surface. So this is kind of what it looks like. This is a rough view though, but if you take, okay, so if you take any piece of like a program, this will be your program, and then it will go out, and this will be the direct 3D stuff, and this will be your OpenGL interfaces, and this will be your OpenGL installable client driver, and so this is the userland graphics driver stuff, right? And they all end up calling, because they have to go to their kernel driver. They end up going to Win32K, and it's very, very thin. It's just a syscall layer. It's 5 instructions basically. It goes into userland, does syscall, and then once the syscall is done, it returns back. And then obviously GDI, it's relatively thin, but it has to do marshalling and validation and capturing all that stuff. So some things do happen here. And then it goes to the DXG kernel, which is DirectX kernel part basically, which is another driver. So both Win32K.sys and DJ and DXG kernel or sys are drivers, but they're really essential parts of Windows. But it's part of the graphics subsystem, so it's technically not part of the kernel or like the core kernel because it's not NTOS. But Windows won't do anything without these things. So they're pretty much always there. And then the DX kernel basically ends up calling into this thing, which is the graphics driver, which is the attack surface, which is what we're going to discuss. But this is sort of a rough overview. There's a lot of layers in between all of this, though. But I think this is more or less captures it. So what does WDM KB driver looks like a skeleton? What's the bare minimum you have to do, right? Somebody writes one and they put it in front of you and say, start auditing. What does it look like? Well, it'll look like, there'll be lots of other stuff in there, but this is it won't do anything without this, right? And this basically means you start off making a driver entry function, which is the way any Windows driver starts. Technically, it doesn't have to be called driver entry. You can give it a different name and have to jump through a number of hoops and it'll still work, but they're pretty much all called driver entry because it's convenient. And then what happens is you fill out the structure called driver initialization data, which basically holds a number of callbacks that say, well, if the user is going to do this graphics operation, or this graphics operation, or this graphics operation, or a number of which, then the Windows indicates this, and the DX kernel will go to your driver and say, it's this operation, then it's this callback for this driver, and it'll call your callback, right? And then once you have that structure filled out, you call DXGK initialize, and that function basically goes to the DX kernel and says, hey, here's my set of callbacks. Now you know about them. When somebody does this operation, find the right callback and call back into me. So the interesting thing about this is that you, unlike almost any other driver in Windows, there are no ERPs, there are no ioctls. It's nothing like WDDM. You never pass the I/O manager. None of that stuff is none of that stuff is there for a graphics driver. It has its completely different path. There's a very similar variant of this, which is basically, so you can make a kernel-only display driver where you have no userland equivalent, and it's a fairly similar callback model, a fairly similar function to call, a fairly similar struct to fill out, but the callbacks are slightly different depending on which operation happens. So this callback, the structure that I spoke of, obviously contains a large number of callbacks. It's 40 or 50, maybe 60, very, very large number. As a security guy, I'm only interested in the things that expose attack surface, right? What is it that I can call from userland where I can pass like raw bytes that I know it's going to parse, right? That's the stuff you care about, right? And so there's sort of there are things that you have very little control over as an attacker. Things that'll happen because so-and-so needs to happen, but you don't get to pass it any data, right? So from a hacker's point of view, we don't care about those callbacks, right? And then there's some where you have some indirect control over some things, and may or may not be interesting depending on what the driver does and how it does these things. And then sort of the third category is sort of where you get to be like, hey, here's a blob of data, and I can pass you 2 gigabytes of bytes, and it'll just parse, right? That's the stuff we care about, right? That's the attack surface. So that's what we're concerned about, and that's what I'll talk about. Before I dive into the entry points of the driver stuff, there's a few things I want to say about synchronization, because WDM has its own synchronization model, and this is interesting to keep in mind. If you go look at these drivers and you see something that looks like a race condition, you need to know this model, because otherwise you'll go like, oh, that's a race condition, and it turns out it's not because of the synchronization model around WDDM. So this is interesting. There's 4 levels to it, and they call them level 3 to level 0. So level 3 is the most restrictive, and level 0 is pretty much wide open. So level 3 is sort of you can't be doing anything basically, right? Only a single thread may ever enter. The GPU has to be idle. There's no DNA buffer process. All video memory has to be evicted from CPU. So basically, if the card's doing anything, you're sitting there blocking until nothing's happening. So 3 is very restrictive. 2 is pretty much the same, except video memory doesn't have to be evicted to the host CPU. 1 is sort of way more liberal in the sense that depending on which thread and from which code pad gets called into it, it gets divided up in these classes, and from each class only 1 thread may enter, and then 0 is basically like completely re-entry. Right? Anybody can call whenever they want. However, and this is interesting to know, because even in this liberal 0 level, concurrency is allowed, but no 2 concurrent threads belonging to the same process may enter. And that's interesting when you think about race conditions, because a lot of cases you'll have these resources that are shared among a process, so different threads will have the same resource, but different processes won't share them. So you'll have a lot of these things that look like a race condition, even though something may be called under synchronization level 0, it just won't be a race condition because of the way it was designed. Okay, so now that we have the entry points, the synchronization stuff out of the way, let's dive into the entry points. I went over I went over a list of them, and they're fairly well documented on MSDN. If you want to know, you can go over them and you can read them, and you'll waste a week or so trying to figure out what all of that means, and maybe longer. So I've come down to like a small list of callbacks where I can be like, yeah, that's attack surface. Like, that's where the bugs are going to be. And so basically, there's sort of four callbacks. One is escape, one's render, one's allocation info, and one's query adapter. Escape is basically the graphics driver equivalent of ioctls. Even the old model had it too, but it was slightly different, but it was the same concept. And so basically, the escapes work by basically just being like, here's a blob of data, and render obviously goes, once you've done something, you say render, and it'll render. Allocation is basically to get like some DMA buffers and stuff done. And query adapter is basically where you can go to a graphics card or the driver and say, hey, give me this kind of information, or give me this kind of information, or give me this kind of information. So before I dive into these, so one of the things I want to get or cover is not just what the entry points are, but how do you get there from userland? Because it's all nice and well to sort of have a list of these are this is your entry point, but how do you actually call into it, right? So before we get into it, I want to just give like a very small, brief look over. How do you write it, initialize a userland piece that gets to a graphics driver, right? And then once I got that, I'll go into the callbacks. And when I go into callbacks, I'll be like, okay, this is the way I'll do it is I'll say, okay, this is the kernel interface, and this is what it does and how it works and where the attack surface is, and I'll be like, and this is the userland function you call to get there, and sort of the order between these things. I know it's a little bit dry, but it's sort of the run up to the fun part, which is where you get to do the fuzzing and reverse engineering. Because if you don't know the first part, you're not going to get anywhere. If you don't know how the interface works, you can't audit it, you can't fuzz it, right? So please bear with me for, I don't know, 15 minutes maybe. So the driver point installation stuff. I'm going to assume that you have done like trivial graphics programming before in Windows userland, and what I mean is like you've used GDI, you know what a device context handle is and that kind of stuff, right? So we start off with a handle to a device context, which is in a GDI world, that's where you start off with. That's your handle to anything you want to do. If you want to print something, you use the HDC. If you want to do something graph, you use the HDC, right? So we assume we come from GDI world, we have an HDC. From the HDC, it's sort of there's sort of three steps you have to do to sort of get to the WDM driver stuff where you can really start doing stuff, right? First thing is you have to, WDM, the callbacks they don't really care about HDCs, they have what they call adapter handles. So you want to go from HDC to an adapter handle. Once you have an adapter handle, you want to get a device handle out of it. And there's a number of things you can do once you have a device handle, but there's also a number of things you can't do until you create a context for your device. So there's basically 2 steps. Right? Once if you have an HDC, step 1 is convert HDC to adapter handle, and then create a device handle out of the adapter handle, and then get a context for that device. And it's a set of fairly simple functions that you call. And so these are the functions themselves. I haven't been able to find any program that or sample code that tells you how to do it, but the functions themselves are documented in MSDN. So you basically fill out the structure where you say, hey, here's my HDC, and then you call D3D KMT open adapter from HDC. You pass it the structure, and if it succeeds, it goes and says, okay, here's your adapter. Once you have your adapter handle, you want to get a device handle out of it, which is a similar process. You fill out a structure, you say, well, here's my adapter handle, and then you call D3D KMT create device, and if that succeeds, you basically get back a device handle. Okay. Right. So, and then the step 3 is to create a context for the device. So the previously obtained, so the device handle you now have is the stuff you pass along to most of your calls to the kernel stuff, to the kernel driver. And so in order to do anything, you need to create a device context for the device. In most cases, you need a device context. Depending on what you want to do, some things do work without a device context. But when you create a device context, things like setting up command buffers that you pass back and forth between userland and kernel, that's what happens when you create a device context. And these are all things the driver does on your behalf. Like it'll do allocations in user space on your behalf that get passed back and forth. When you create a device context, there's always some attack surface here. So when you make this call to kernel, you get to provide a pointer which says, okay, here's data, and you get to provide a size and says, okay, here's data. And it's not, so that pointer and length is up to the driver to do with it. They can do with it anything they want. The documentation doesn't say that it has to be structured anyway. It's just a pointer and a length. Most drivers I've seen at this point don't really do much with this data at this point. But it's up to the driver. So some drivers may just take that data and just implement an arbitrary protocol and start doing all sorts of parsing. So there is potential attack surface when you create a context. But it's completely driver dependent. So this is basically, it's the same, the similar concept as before, where you fill out a structure and then you say, well, here's my device handle, and then you call KMD create context, and if that succeeds, then you get a context, and the structure you pass basically is this thing, and so these are the interesting ones, right? Is private driver data size and private driver data. If the driver has a parser for that, that's attack surface. That's stuff you care about, right? If you're going to write a fuzzer, those are things you want to fuzz. Okay, and then yeah. So when you're done, so these are sort of the output buffers. So this is when you create a context. The driver does a number of things on your behalf. So it'll create a command buffer. And it'll map it into your address space. So you don't get to map it, but you control it, and it's in your address space. And this is the buffer that's going to be used when you send commands back and forth between user and kernel. That's the buffer that's going to be used. And then we'll talk a bit more about that later. But these are sort of allocations, stuff that happens when you create a context that the driver does on your behalf. Okay, so now that I've sort of covered the sort of, how do I actually get to talk to this thing? Where do you start? I'll talk about the 4 entry points that I mentioned previously, which is escape, render, allocation, and query adapter, right? So I'll start off with escape. The callback is called DXGK escape. And as I mentioned before, this is the ioctl of graphics drivers, right? So if you're familiar with general Windows drivers, obviously ioctl is usually the main thing where you go and look for bugs. Graphics drivers, it's escape. It's a similar concept. It's just the arguments are different. This is very much like the old. So if you had the old display model, there's a function called xescape, this is pretty much the equivalent of that. However, xescape sort of separates out a function number, and then you get a blob of data. And for WDM, that's sort of there's no type anymore. There's just a blob of data. So what that means is there's no structures, there's no predefined protocol at all. It's the driver is free to implement it any way it sees fit. Yes, MSDN describes it as that function shares information with user mode and display driver, but it's the graphics driver ioctl equivalent basically. And this falls under threading level 2. So race conditions in escape callbacks. Unlikely. Not saying it's impossible, but it's unlikely. So what does this look like? Well, the kernel interface kind of looks like this. So if you're going to audit a driver, if you have implement one, you basically the callback will have this function, and it'll look like this. And this is the sort of the predefined how this function looks like. And the thing you care about is the second argument is a structure that gets passed on. And it'll contain a handle device and a couple of flags and a context. And from an attacker point of view, generally those are things you don't really care about because you don't control them. But the interesting parts is obviously the driver data and the driver data size, because that says this is stuff that came from userland. This is attacker control content. That's potential attacks. Anything that touches that has to do extensive validation, or or things will go very wrong. So yeah, a few more things about this. I started looking into it because I wanted to see what the conditions are around this data. And so this private driver data is probed and captured. And if you don't know what probed and captured means, is that these are kernel concepts that that are or terms that come from the Windows world for kernel concept. Probed means that before the data is handed to you, the Windows kernel has made sure that this piece of data that you pass from userland, that it's valid, and that it's in userland range, and that it's mapped and all this kind of stuff. And captures means that once they've done that, it's been mirrored into kernel address space. So what that means is that while you as an attacker control the content, you don't control the memory region itself. You can't unmap it while the driver's trying to do things. All those problems don't occur because it's probed and captured. But beyond that, you as an attacker have full control over the content. Between sending this from your userland function to the actual driver, there's no validation of the content that happens. So every bit ends up in this interface, in the private data, that's attack surface. You control that. Prior to this function, it's never been validated. And there's no length restrictions on this. So one of the things is usually when you have these kind of interfaces, one of the things people tend to do is, when they do this kind of like probing caption, they'll be like, well, we'll put a link restriction. We'll say, well, you get to use, I don't know, 10 pages or 100 pages or whatnot. In WDM case, there's no link restrictions. Because the driver data size is a uint, technically there is a link restriction in the sense that it's restricted to 4 gigabytes. But 4 gigabytes should give you enough attack surface, right? And so the probing capturing is interesting because it means you don't have to do any kind of validation because the memory is already there. Of course, if the protocol allows, the protocol between user mode and kernel mode allows for any kind of embedded pointers in that length, then obviously those pointers still need to be validated and probed and captured and so forth. So how do you talk this stuff from userland? Well, it's as before, basically, it's a function called D3D KMD escape, and it has a structure, and the structure is on MSDN. And again, so the structure isn't exactly the same, but there's, they look very similar, right? There's an adapter handle and a device handle and a type and flags and a context. And these are things, obviously, as I said before, that where there isn't that much attack surface, but it's the driver data and the driver data size that are interesting and important, and that's where the bugs are going to be. And it's really not like it's a function, but it's really just a system call. There's nothing happens. So what's funny is that if you look at this thing in IDA and you look at the export table, it's called D3D KMD escape. But then if you go to the Microsoft symbol server, the symbol server comes back and says that's not D3D KMD escape. That's NTGDI DDI escape, which means it's a system call, right? It just happens to be one that's exported under a different name. So these functions are really just, it's very raw. There's the layer between user and kernel where you hand off your data, it's pretty thin. It's 4 instructions, right? Right. So that's sort of the dry entry point for escape. As for render, it's a similar kind of callback. This one happens basically when you want to render something, you go and say render, right? This is the hard rendering, allows you to Motel GPU render from a command buffer. It's sort of a similar concept where this is your callback and this is the structure you pass it. And so the command and this patch location list in, this is stuff that's set up on your behalf when you create a context. And what's interesting about these is that both command and patch location list in are mapped in userland, so they're mapped in your address space. So you don't control the pointer where it's mapped. That pointer is fixed, but it's in your address space, and that is interesting in the sense that when the driver has to touch it, because you can still have a second thread in userland where you say, oh, while it's fixed, I can still unmap this thing, right? And then if your kernel equivalent doesn't account for the unmapping, still bad things can happen. And the other thing is because it's in userland, you can also have, even if you account for this unmapping, you can have all these race conditions where, because you'll validate something in that structure, like you'll validate something in a command buffer, for example, right? Say byte XYZ has to be this value or this value. And then after you validate, you can have a second thread in userland that just overwrites it, and all of a sudden your validation is no longer valid. So it's interesting to note that while the pointer is fixed, you can still sort of change the content underneath the driver without their knowledge. Right, so command buffer and patch location go from userland. And so actually, what's really interesting is that MSDN says, specifically notes this, right? They say, well, this comes from user multiplayer driver, and so this way Miniport driver must use try except code to handle this. Otherwise, if somebody maps it, then you crash. And WDM actually gives you, MSDN actually gives you, gives you sample code for how to do this. And initially when I looked at it, before I fully understood the create context, I was like, well, if they come from userland, shouldn't you be probing and capturing your stuff before you do this? And because afterwards I was like, oh, create context actually maps this stuff on your behalf, so you don't control the pointer, it just happens to be in your address space. And so there's no probing that happens here because it doesn't need to be probed, it's already been probed. But you still need to do a try except. Yeah, so userland doesn't actually get to do this because, right. Yeah, I pretty much covered the slide, awesome. So I have an example of how to do this, and actually this is from a real driver, and this has already been fixed. So this is from the VirtualBox driver, and so this is the render callback, and they basically go, well, this is your private data buffer right here, your command buffer right here, and then they say they touch this stuff, but there's no try except. So this can obviously blue screen, right? And this comes from a real driver, so this is real code that has done it wrong, hasn't done what MSDN said you should do. So that's one example of not having a try except. That's one example. And so here's another example of the same driver in the same function where this isn't just a crash, this is sort of a race condition, right? Where you get sort of a time of check, time of use condition where this pointer comes from the command buffer, and then there's this validation that happens here. And then after this validation, that data gets used. But because it points to userland, between validation and between use, I can have a second thread and just overwrite the data. And then all the checks that happen here are no longer valid. And this is the same driver, different bug. This one has been fixed too. This is both of them are VirtualBox, and I believe Oracle fixed them in a CPU in April. So it's been fixed for a while. So because their driver's open source, I used it to sort of start off my research and sort of guide me towards what these things look like. Because it's easier to read C or C++ code than it is to look at IDA and go like, I wonder what this structure does. Right. So how do we talk to this thing from userland? Well, it's kind of the same thing, right? There's a function for it, and there's a structure, and again, the structure isn't the same as the kernel structure, but it's very similar, right? So when you go from kernel to user mode, there's sort of this translation between these structures that happen, right? But it contains the same kind of information. And again, it's really just, even though it's a function, if you go to the symbol server says, actually this is just a very thin syscall wrapper. Okay. So allocation. So this one basically does allocation on userland's behalf to allocate memory, and it's either system memory or video memory depending on which flags you set. And so the kernel callback basically it's called DXGK, DDI create allocation, and this is fairly similar stuff to the previous three ones I covered, where the second argument is the structure, and the structure basically contains a number of things that you as an attacker have very little control over, but it also contains a private data pointer and a private data size, which, again, as we know, that's attack surface. That's completely up to the driver how they want to implement it and how they want to parse it. And the data is completely controlled by userland, right? And then, so there's a second structure in there, which is p allocation info, and so you can have a list of p allocation info numbers, and each one of those will have their own private data size. So you can have a private data size and then a list of private data sizes, and all of this is attack surface, and all of it goes through like one system call. So there's a fair amount of potential attack surface here. Right, yeah, let's cover this. Okay, so how do you get this from the userland? Same kind of thing, right? There's a function for this, and there's a structure which isn't the same as the kernel one, but it looks very similar. And again, if you look at it in the assembler and you go to the symbol server, Microsoft symbol server says actually it's really system call, and it's and it's these four instructions. Okay. So now the fourth one, query adapter. Query adapter is a little bit different because so the previous three I covered all have these these input buffers where you go into the driver and say, well, parse this, parse this. So those are, I can see your entry points, right? The thing I found interesting with Query Adapter is that it's not so much entry points as it is the exit points. So you go to the driver and you say, hand me this back. And depending on what you tell it, some of them have these predefined structures that have to be this big or so forth. But some of them can have these blobs, right? And when you get blobs back from kernel, it's so interesting when you start inspecting them to see if you can find like a member in a structure that wasn't initialized, or some kind of compiler slack space that was added somewhere, or bits and bytes or ranges of bytes that were never written to, and so you get these leaks of uninitialized kernel memory back. And so I've seen a few of these in query adapters. And so yeah, same deal as before, right? There's a function for this, and you there's a structure you pass it. And so there's an input buffer and output buffer, because so depending on which query adapter, there's a type you say, and depending on which type, it'll expect different structures. So some will have input and some will have output. Actually, most have output, but only a handful of input. So yeah, as I mentioned before, it's interesting entry and exit points. This is data that is being passed in from userland, but more importantly, it's the exit points are the things that are interesting, where you get all this data back from drivers. And just if you start looking at these things, like every so often you'll see something where if you do the same call 5 or 10 times over, like there'll be like this range of bytes that like just randomly seem to contain garbage, or maybe there'll be some structure in one but no structure in the other, where you like go like, well, that one looks like it's an information leak, right? And then you go look at the driver, or you go look at the assembly or code if you have it. And quite often when you have those kind of situations, you'll have an information leak. Okay, right. So how do you talk it from userland? Same procedure, right? There's a function for this, and it's a structure which isn't quite the same as the kernel structure, but they're very closely related. And again, it's even though MSDN says it's a function, it's not really a function. It's a system call. So yeah, when I started looking at some of these drivers, there's a number of things I found and I haven't really gotten all that far drivers because there's many of them, and the lead up of these things sort of took a lot of my time. But when I started looking at them, there are sort of 3 things I found that were fairly obvious, where that I think and these, it's not like these are new, but it's sort of I want to reiterate to make sure that if you're ever going to be involved in writing a graphics driver, please keep these things in mind. First of all, out of bound read or write, right? When you take a buffer where you know data comes from an attacker, right? Every bit counts, every byte counts, right? If you take the buffer and you read out the first or the second byte and you haven't validated that the second byte is there, you just assume, that's wrong, right? In userland, you might get away with it, right? In kernel mode, you don't, right? That reading that second byte can be a blue screen, right? Because the first byte could be at the end of a page, and the second page couldn't be mapped, and all of a sudden you get a blue screen, right? So these things really matter when you write kernel code, right? And out of bound writes are usually something where if you're a developer, you go like, well, that's memory corruption. We understand it, and so people tend to be very careful with those things. But out of bound reads, people tend not to be very careful with that, even though you still end up with a blue screen. So that's very common, and I wish people, when they write kernel code, go like, even out of bound reads, you have to be really, really careful. That's one. The second one I saw is, and this was through a lot of drivers, surprisingly, is that it won't be like the debug code, but it'll be like the debug functions themselves will be gone, but all the surrounding context for debug code is still there. So you'll see these creation of strings saying, well, function XYZ does this, and it's supposed to do so and so. Even though it will never get printed, the strings are still there. And so if you're a reverse engineering driver, that's very, very useful, because all of a sudden you're telling me what your driver's doing, and I don't have to spend a night looking at all this weird assembly. So when you make a driver and you ship them, make sure you delete all the debug code, and not just the actual print call, but the surrounding code as well, to make sure that you don't make it easier on people than you have to. And the third one I saw is, can't remember which driver it was, but one of them made sort of their own library of all these integer overflow routines, which, let's just say that it was there, and rolling your own for these kind of safety routines is generally a bad idea because one mistake and it doesn't, and your entire safety goes away, right? Whereas the Windows kernel has its own integer library routines, and it's sort of a fixed point, right? First of all, they're very, very well tested. It's highly unlikely there will be a bug in the Windows integer library routines, and even if there are, it's not your fault. It's Microsoft's, and they'll fix it if you find one, right? So don't roll your own. Don't use don't make your own integer overflow checking functions. Use the ones that are in kernel. They're available to you. Stuff like RTL, uint_add, and so forth. Use those. Okay. Right. Okay. That's the dry stuff. Awesome. So so now writing your full user to talk to the kernel. How does that work? Well, turns out it's slightly more difficult than I thought it was because while the APIs are documented in MSDN, the actual headers, they're not there. You can't find them. They're not anywhere. And this is mostly meant for OpenGL installable client driver stuff. So unless you're writing that, you're not really supposed to be calling these things, even though they're exported. And so there's a dev kit for this, and then MSDN says, well, to obtain license, email this team and so and so. I didn't do that because I wanted to get sort of the hacker's point of view for this without having that. But because these structures are documented in MSDN, getting like a partially working implementation is really easy because you just copy paste from MSDN to your editor and it works. Or if you don't want to use that, you could use the COM APIs, but I'm not a huge fan. Anyway, once you have those headers working, it's just a case of load library, get proc address, and you can just start using these things. Okay, so once you have a full program, and I did all these tests, what I really want to do is write a program where I could hook the APIs and see, because every driver is different, right? And so I want to know what the protocol is between UMD and KMD. And the only way to really see that is to sort of start snooping data, see what real data looks like. And so I wrote a small utility to sort of be like, where I hook escape, render, create allocation, and create app info for a driver, and then see what happens and where that happens. And so I will see if I can demo this. Keep your fingers crossed because demos don't always work. So the best program, or an easy program I found where you can easily snoop data is the Microsoft PowerPoint viewer, because it's all graphics, and every time you do a slide transition, there's all sorts of rendering that has to happen, and you control the transition, right? Because you get to say when the slide goes. So I used Microsoft PowerPoint viewer, and that thus far has worked pretty well. What I first wanted to do is I wanted to have like a stock vanilla Windows without any kind of graphics driver that is just the Windows. And I thought I had one of those in the VM. Of course, I wake up this morning an hour before I have to do the presentation, and I can't find the VM. So I can't actually show you what a stock Windows looks like when it does these things. Or I can't show you, but I can tell you. Basically, for every slide transition, if you have a stock Windows without any kind of more advanced graphics driver, you'll see for every transition there will be like one call to render, one call to render, one call to render, and that's pretty much it. This is an old netbook that I have. It has an old AMD card, but you get to see all the magic that happens, like the true magic of what these cards do, like the stuff that happens behind your back, but that makes things much better than if you just use standard Windows cards. So I picked some random presentation of the internet. I don't know what this is, but and then you hook it, okay, and let's hope this works. You do a slide transition, and this is all AMD driver magic that happens behind your back, right? And this looks slow, but it's only slow because I'm hooking it, and my tool is really, really slow. But you'll see. So this is all. So you see, this will be an escape, and all these bytes here. That's AMD. That's AMD protocol, right? That's user goes to driver and says, do this, do this, do this. This isn't described anywhere else. This is. And nothing. There's no spec that maybe there's, but there's no public spec that says it has to be this or this or this. And so now, once you sniffed it, this data is really important because once I know what these bytes look like, I can try to mimic it and see if I can get any bugs out of it, right? So that was my tool. It'll be released. It'll be released on our website, hopefully today, but I can't guarantee that. But anyway, it'll be released soon. So now we have all that. Putting it all together, right? So fuzzing. So once we have the snooping tool, creating a mutating fuzzer is relatively easy, right? You take, oh crap, hold on. There we go. Right, so I did this. So yeah, putting it all together, fuzzing and reverse engineering. So once we have this the snooping tool, you just take the data I just showed you, and you can sort of write a tool around it and says, well, you take that as your template, right? The valid bytes, you saw which sniffer, right? You know that's valid because that was AMD client talk, AMD userland talk, AMD kernel, and it succeeded, so you know that's a valid. And so you try to take that and then mutate it and see if something happens or if nothing happens. So I build a small fuzz around that does that. And so you basically do that in a loop until hopefully something crashes. And if it doesn't, you can. If it doesn't, I'll get back to that in the next few slides. But I also have a small demo of that, and I hope it'll work. But okay. Okay, let's see if this one works. Yeah, there we go. There we go. So that if you just start mutating this stuff, these things crash. And so I did report this to the AMD guys, and they have fixed it. And I was told that there's going to be an update somewhere in August this month. You probably might know more about this. Right. So the problems in this AMD driver, the problems that I found with this fuzzer, been reported to AMD, and they fixed them. And I think the patch are coming out somewhere this month. Yeah. So they're coming out a few days, few weeks. So this stuff's going to get fixed soon. So this is how easy it can be to fuzz this stuff, right? So you basically do this in a loop, and then bugs come out. So sometimes reverse engineering will be needed because you want to see what the bug looks like, what it is, how it works, right? And so there's this book about reverse engineering that came out a few months ago, and my buddy Bruce Dang wrote it, and he had this interesting quote which I just had to put in here. Oh, God damn it! Yeah, there we go. So that says, if the process of reverse engineering Windows drivers could be modeled as a discrete task, 90% is understanding how the thing works, and only 10% is understanding assembly. That is, all the build up until this has been there because otherwise you can read all the assembly you want, you don't know what it means, right? Now that we know what the callback looks like and we know what the arguments look like, reverse engineering stuff is trivial, right? It becomes really easy. So I showed before, right? You do this DXG initialize and you pass the callback. And this stuff is actually a little bit tricky when you look at it the first time in assembler because DXJ initialize is an inline function, which means you don't go out and call it. There's no symbol for this. It's assembly that gets sort of mapped into your image, right? And so you basically I made a debug driver, so that's because you get to see the symbol because it comes with a PDB file. But usually you just see a call to an address. So what does it look like? Well, you get this call to this function, and then this function basically, you'll see this. Okay, so basically what happens is how does this callback really work? Well, it goes and loads the DX kernel. It's usually already there, but in case it's not, it gets loaded. And once that thing is loaded, you get a pointer to the device object, and you do an IOCL in that device object, video device function 10, method neither, finding access. I don't know exactly what that does, but that's what this function does. So, and then it hands you back a function pointer, and you call that function pointer with the method you registered, right? And I'm saying this because the stuff's inlined, and so you won't see that call. You'll just see these set of instructions that do this. So when you see this or these set of things, that's when you know a callback the set of callbacks get registered. The table itself is interesting because that's where you find the callback, right? That's where all your points are, so you want to find that thing, right? It can be created or stored in different ways, and it's usually pretty trivial to find these things. It'll be, they'll be filled out on the stack, or they'll have some dedicated function to fill out a global array of these things. They're usually pretty easy to find. Like it'll look something like this, where like this will be a dedicated function that just writes a bunch of callbacks to a global structure, or this is something that writes to the stack, and then that pointer to that array gets handed back to the kernel. And the actual structure looks like this, right? It's basically just the structure of all these callbacks. And some of which are, there'll be escape and render and query adapter and so forth. And so mapping the structure back to the IDA stuff is pretty easy, and I started doing it here. But this stuff is pretty easy. So once you get to the stuff where you get the private data handling, right? This is where it gets interesting, and this is sort of where once you see that in a disassembler, it feels very much like you're looking at a network protocol handler, where you get a pointer and a length, and it'll have like it'll generally have like a header with like a type length value, and then it'll, based on whatever the type is, it'll call back into all these things, and you'll see like a switch case, right? This is one driver. I can't remember which one it is, but it's pretty much where they'll go, well, this is the callback, and then this is the type, and then for every type, there's basically not a function that gets called, right? So this is pretty standard stuff. Like once you get here, like you kind of start smelling the bugs. You're like, where's the good stuff, right? So that this is when you start seeing these things that I tend to get a little bit excited. But once you get there, that's where the good stuff happens, right? So when you start combining this with runtime testing, one of the things you want to look at is sort of the return values basically tells you either failure or success, and then success is usually 0, and success will be any number of anti-status codes. Usually the one you see the most when something wrong happened is status invalid parameter, which is 0xC, bunch of zeros D. And when you fuzz the stuff in a loop and you see everything comes back with just status invalid parameter without anything else, that usually means that the driver has some kind of very early on length checking. I've seen some of them have it, some of them don't. I think this one came from the Intel driver. And so basically this function got called immediately after the DXG callback. And basically, you see basically that they say, well, driver size has to be at least this length, and the length has to match exactly with, I'm almost done. The length has to match exactly with this embedded length field, right? And once you see that piece of code, you can be like, oh, well now, if I just implement this logic in my fuzzer, you get past all this stuff, and all of a sudden you run the fuzzer and there's like immediate blue screens, right? So if you see this behavior where just everything stands invalid parameter, just go look for that early bound check somewhere. Because once you get past that, the fuzzer starts finding stuff again. So yeah, as a summary, so pretty much almost done. Yeah, WDM has been around since Vista. It's evolved over time. There are several interesting trust boundaries and entry points, escape, render allocation, query adapter. There might be a few others, but I just haven't gotten around to it. Like in WDM for Windows 8.1, there was support added for Miracast, which is this remote display protocol, which may have interesting attack surface, but I haven't gotten there yet. Most of the attack surface control data sent from Unity is not standardized anyway. Driver gets implemented any way they want, which is interesting because that's your attack surface, right? So it's not structured like WDM drivers. There's no warps, there's no ioxels, there's none of that. You don't know what the last one. Okay, so as a conclusion, this has been pretty much untouched attack surface up until now. I started looking at this stuff, and you make this fuzzer, and most of the drivers you tried against, they'll all fall at some point. So it's interesting to see that it's untouched attack surface, and so there's work to be done here. But I think it's going to get better. So I reported to the AMD guys, for example, and then they fixed a bunch of these things. And I reported to some others, and they're working on patches too. So I think it's going to get better. But at the present time, it's not great. And so there's some work to be done. But it'll get better, I think. Anyway, that's it. Anybody have any questions? Speak now or forever hold your peace.
What do you think about the general design itself?
So your question is what I think about the design of WDM in terms of entry point and attack surface? Okay. There's some things I liked, there's some things I didn't. Whenever you have like probing and capturing, I think that's good because it takes away a lot of the attack surface. I think things would be, you'd have less attack surface or things that are more easily checked or controlled when you have a more structured way of passing data. Of course, the downside of that is that you as the driver developer lose some control, right? So it's this double-edged sword. The other ones, of course, stuff like when you do a render and you get all these userland pointers, there's a lot of extra checking that needs to happen. And obviously, you could optimize that and do probing and capturing, but then you lose performance, right? So you get this weird trade-off. So I think overall, I think it's good. There's very few things where I go like, this one's really bad. But you can see where the guys who designed stuff at Microsoft sat down and said, well, this is a trade-off, right? We could do this better for security, but it would cost us, right? And if you're talking about graphics, you want performance, right? You want that stuff, right? So some trade-offs have to be made. I think it's pretty good. From a security point of view, I like it. Yeah, there's things that could be better, but the previous model was a lot worse. So I think it's pretty good. Okay. Did I answer the question? Awesome. Any other questions? Okay. Oh, yeah. Am I going to read the fuzzer? That's a good question. So I haven't made up my mind yet. I'm planning to at some point, maybe. I think if I do it right now, it'll piss off a number of people. I want to release it. Trust me, it's a question I've asked myself for a while, and hopefully at some point. But I can't say that right now. Any other questions? Awesome. Guess I'm done. Thanks for listening. Hope you enjoyed it.